I'll start recording. Okay, I'll kick off with a short introduction. So thank you everybody for attending the Global Technical Inserto Reading Club. Today is a meeting on, it's basically the first meeting on entropy. So we have a talk today from Marcus Carrera on Introduction to Maximum Entropy, followed by a discussion with Nassim. So just a bit of background on the Reading Club. It is a reading club that happens every few months or so. Once we get going, it's perhaps every month. But previously we've discussed the statistical consequences of fat tails, and that was a monthly event going through the main chapters. Books available at this link here. The intent is to review Nassim's next book on entropy.
No. I mean, it's not, no. It's not about me. It's about It started with statistical consequences of fat tails, and it will continue with Marcos's next book. All right.
There's a website here, which special thanks to Jake Billings, who has produced the website. So all the recordings for previous events and code and discussion and so on, all on that site. There's a GitHub repository containing all the code as well. Special thanks to all the contributors to date. So Marcus, Fergal, and Nassim, and also Ron, who's not with us today. And with that, I will hand over to Marcus to take us through the first topic.
Okay, let's. Okay, can I start sharing the screen? Okay. Okay, can you hear me, James?
Yep.
Okay. So I hope that everyone is, the screen is okay. I'll try to get it to slideshow. Okay. So today's talk is meant to be an introduction. We want this. We'll just discuss briefly things today. There's not much previous material. So before we had the whole book. Now the main material is Nassim's paper. We did that and Donald Gannon, and some papers and books on maximum entropy. We will work out some things as we go. We will discover some of Nassim's notebooks and papers and stuff that he's working on entropy, and we will refine things as we go. We will try to skip through the maths today, so we just show briefly what they look like, but the idea is not to get into that much detail today. So first thing is the definition of entropy. So when we have the discrete entropy, think about some possible event. Each event has we have an event. Each event has a probability pi of happening, and then when we calculate that formula, we have a function that has some interesting properties, and one of them is always non-negative, and we can have a similar definition for continuous entropy, which can be negative, and it's always relative to something. So we can be also called differential entropy. So the idea is to measure how much information we have in the system, how much knowledge we need to get to in order to find something. So the higher the entropy, the more disordered is the system, the higher my ignorance about the system. So when I can think about information gain as a decrease of entropy. So suppose that there is an example of a problem in which there is a right choice of answer among many possible known answers. And we will want to reduce our uncertainty with the lower effort. So, or choosing the lowest number of features possible. For those who know a bit of machine learning and know about decision trees and then how to use decision trees into random forests and stuff, the idea of a decision tree is I want to find the features that can help me to separate my classes in the most efficient way. So my cost function is also important. So I want to have to maximize to minimize the number of questions asked, or I want to have the lowest number of misclassifications and so on. And an example that most people should be familiar with is Wordle. We have one choice of known words, and each test word that we use, given the answer, reduces the set of possible words. It's easier to there are two nice videos from the Tree Blue One Brown channel that describe a procedure to use the information gain to create a Wordle solver. The easiest thing for us to do is at each round, I want to get the highest reduction in entropy. So let's say that I have 4,000 words, 5 letters. So this will be something like 2 raised to 12. So let's say that if I use my base on the log as 2, I have 12. My entropy is 12. I have too many possibilities, but I want to reduce that 12 number to 6, and I want to reduce it to 3, and then I want to reduce it to 0 because I want to know, okay, what is my last word? So programming a Wordle and looking at how to program Wordle is useful to get the idea of entropy and information gain. And also to program a game solver is more fun than just playing it afterwards. So what is the principle of maximum entropy? So we have families of different possibilities for functions, families of functions for the probability densities of our answers. So given some constraints, the most common ones are constraints on the mean, or the variance, or others constraints. So the answer to the principle of maximum entropy is that the distribution, we want to find a distribution that follows those constraints and has the maximum possible entropy. So let's look at the examples of the Brandeis dice. There are some philosophical questions about it, but we'll just use it as a simple example. So we have repeated throws of a die that might be weighted, so probabilities are not uniform. So we are given the average X of a large number of throws. So, and we want to calculate the expected probability for each of the 6 numbers on the next toss. So what do we do? So if we use Mathematica, we create a function. So we want to, so we know that the weighted average, so given the probability, I know that the weighted average of the dice is the X number that I have found. So if 6 has a higher probability than 1, I would expect that number X to be higher than 3.5. So this is the constraint, this is the information that I'm giving you. And this is the entropy function. And this is, of course, the basic condition that our probabilities must amount to 1. So we just
Marco, Can I just jump, just to give intuition for people, for our friends here who are not quite familiar with the concept?
Yes.
With a very simple example. Okay, let's take, well, can you, if you see the board, let's take a very simple example, very simple example. Where on earth is Marcos? Okay? You want to find where is Marcos related? Okay? So here we have, let's say that we're dividing the world into uh, 16 squares. Okay, we'll take this out. Okay. Divide the world 16 squares. We have no idea where you're going to be. Okay. So pretty much entropy is going to be how many questions, should I ask to know where Marcos is? Okay. So my first question is it west of west of Beirut? Yes or no? Where are you? West of Beirut? Yes or no, Marcos?
Yes. Yes.
Yes,
West
okay.
of Beirut. Yes.
Question one. And then you say, okay, are you north of the equator?
Yes.
Okay, north of the equator. Now you're here, okay? And then I say, are you west of Paris?
West of Paris. Yes.
West of Paris, you're here, okay? So now we know he's west of Paris and north of the equator, okay? So I'm gonna say, are you north or south, north of Brooklyn?
No. South of Brooklyn.
South of Brooklyn. Okay, very good. So now here you are. So we asked 4 questions, okay? Because basically the number of question is 2 to the 4, no? That's 32, sorry?
16.
Yeah, the 16. Okay, you have 16 holes, okay? So if we take, so basically 4 is the entropy. So log base 2, okay, of the number of choices you have is going to be the entropy. It's binary entropy. So when you move to the other entropy, which you called differential entropy, we no longer use log of base 2 because it's pretty much the same. You can use the natural log. So does this give the intuition?
Yes. And
So-
every time,
I have to ask to know where you're located, the higher the entropy, and and it grows logarithmically.
okay.
So sorry, I interrupted.
No, no problem.
For
Yeah,
instance,
so yes, it's the
Yes, go
idea
ahead.
of so that's the idea of Wordle. So, and some problems are better structured in terms of helping you to find questions easily. Some others are not. So this is a very simple example. So let's go back to
So we can get from the example that entropy is linear, okay, to the log of possibilities. You see, or is actually equivalent to the number of questions you must ask to know where someone's located. So the more complexity you have, the more difficult it is, the higher the entropy.
So, coming back then to the example of the function. So, given this is the discrete case, so we are just summing the 6 possibilities. We know that they must add to 1, and we know this average. So, and the average because so this is the value of the phase, and this is the probability. So we have this function to maximize given this constraint and this constraint. And once we ask Mathematica to maximize that, so we go back to the original point, and the confusion that some people have when they look at, oh, if my average move it from 3.5 to 4.5, so I got rid of 1 and 2, so I'm just doing an equally weighted average of the higher numbers, 3, 4, 5, 6. And what we find is that no, because the maximum entropy distribution is in fact the one closest that is closest to the uniform distribution, given that, because the uniform because without this constraint, if I just cross out this constraint, the function that maximizes the entropy is the uniform distribution. So
Actually, it's an easier intuition here is to say that if I have a die, you know, a Bernoulli with 2 probability P and 1 minus P, you maximize entropy, which is P log of P plus 1 minus P log 1 minus P, and that's maximal for P equal 1/2. P equals 1 minus P equal 1/2. So when you have equal, maximum ignorance comes when, for example, if you go back to this example here, you have the maximum entropy if all squares have equal probability. You see? But if some square have lower probability, so the average number of question odds are I'm going to have to, you know, ask, it is reduced. And if only one square has 100% probability, I just have to ask you no question. You see, so the entropy is maximal where you have equal probability. So this is the case of uniform in this case, and also the case of uniform in the Bernoulli, no?
Yes, and because you try to look for the distribution that even while, let's say, following this constraint here is the closest to the uniform, that means that it gets really hard to get rid of possibilities. So one of the interpretations of the maximum entropy possible is that when you look, especially when you're looking into discrete probabilities, that means that you need to have your constraint must be really strong to make one of these probabilities go to 0. So the easiest thing then is to look at this. So depending on the average, so if the average is 3.5, the probability of 1, 2, 3, 4, 5, and 6 are all the same. But as my average goes up, I see that 1 still has some probability. It's only when I go to 5.5 or something that I say, okay, now 1 is definitely out of the question. Then you can see that it takes a lot of effort to get 2 goes to 0 almost at 6. So if we follow that principle of maximum entropy, these are the answers to the problem given a particular average, 3, 4, 5, whatever. So what we are looking for is that slice, the probability distribution given a particular constraint. So if I take the slice here and say, okay, my average is 4.5, then I have a really high probability of 6, and then 5 and 4 and 3 and 2 and 1. And if I just rotate this graph, I'll see those different slices. So another thing that we tweeted out was an explanatory paper written by Kate Conrad, in which he describes the ideas behind maximum entropy and probability distributions. So there are 2 approaches that we can follow here. One is we want to look at a particular distribution, let's say an exponential distribution, a Gaussian distribution, a student T distribution or something. So we know the distribution, we want to know to each maximum entropy problem this distribution applies. So we are given the distribution T and we try to find which constraints on the original data distribution are needed. The second approach is we maximize this function here, but instead of using Mathematica to do that, we use Lagrange multipliers and find the distribution or the family of distributions. The first approach looks like that. This looks like the entropy integral, but we have two different distributions here. So let's say that I want to look at the exponential distribution here. And when I calculate this integral here and the limits of integration go 0 to infinity, I find this. So that term here is the mean of P. So the idea is, okay, I want to probably, if I give you information about the mean of the distribution, that means that I'm probably going to get the exponential or distribution as the maximum entropy probability. So
you're setting just the mean of the distribution as a constraint and no other constraint.
No other constraint.
Okay, so you end up with the exponential. That's go ahead.
Yes. So the idea is that I give you, okay, if I put on some distribution in Q, I get some integral, which is the kind of the fixed value that I want. So
yeah, so basically what Marcus is doing is you say the following: I have a function, I'm maximizing the log of that function or negative the log of the function, okay? And that function integrates to 1. That's the first. In other words, the sum of all, the densities integrates to 1. It's not a sum of the densities integrates to 1. That's first criterion. And then you add other things. The integral of x f of x, which is the mean, okay, equals m, all right? And then with the exponential or equals lambda, and the exponential, you get the function can only be e to minus lambda times plus something, okay? And then you can reduce that and result. So finding the maximum entropy distribution has more philosophical dimension when you talk about the Gaussian, because Gaussian is precisely the product of maximizing something conditional on the existence of a mean and the existence of a squared deviation.
Yes.
Hence the Gaussian, and that is what is shocking about this method, is that we recover central limit without knowing that things that have to have a variance, okay, that's finite and have to have a mean, will necessarily be Gaussian under maximum ignorance. Sorry, go ahead.
Yes, of course.
And by the way, to tell everyone, we changed it. I refused this to be about the incerto, to change it to global uncertainty. So now we're talking about the books of the other parts of the group. I've done my job. I want to go into cycling. So you guys got to write books so you can comment on them. Okay.
So as Nassim was saying, so you see that if you're calculating that square deviation, it means that you know the mean. And we spend a lot of time discussing, well, we only know the moments of the distribution of our data under pretty kind of limited circumstances. So the idea of our fixed, it's going to be really hard to know something as complete as this stuff. how can you be sure? We spent a lot of time discussing that the second momentum is not something that is going to be nice and converge and everything in the kind of data that we deal with. So our ignorance is probably bigger than we try to make it. But what we can know or suppose is probably going to have a different shape than those integrals. And we're going to get a kind of look at it, a peek at it when we discuss the Gammon and Taleb paper. So, and if for those interested, if you go to Wikipedia, there is a bunch of distributions and they say, okay, this distribution has this domain and the mean has this formula, or what we know about it, the constraints is this formula.
Exactly. So basically, if you put no constraint, all right, if you put no constraint on a distribution, what do you get? Cauchy. You're maximizing the distribution, the entropy. And if you put the log constraints of log of, by constraining by log of the variable, you maximize, guess what you get? You get the power law.
Yeah, so this is the kind of thing that we want to delve on the further chapters, which is, let's look at these distributions and pair them with these constraints, work out the math and see, okay, what is the domain which we can apply it and such, so we can use it in practice. Because we are not going to focus on the distributions that they used in physics, because some of them are there in the Wikipedia table, but things like power laws are. It
is worth mentioning. It is worth mentioning that there exist different entropies. What we're talking about is simple Boltzmann, later on Shannon entropy. But there's such a thing as Rényi entropy, and then there is Tsallis entropy, which is for things that are not additive, for environments that are not additive. And these produce something called Q Gaussian, which effectively turn into student T, which are power laws, which are fat-tailed. So in physics, they're more sophisticated in using these, they call it non-extensive entropy methods. It's a technique that we don't need to bother with at this point in the discussion, but at some point, in entropy, open entropy one, we should discuss it.
Yes. So, for example, there is a paper in which the author shows how do I get the student T as the maximum entropy distribution. So this is a good paper for us to delve into.
Yeah, but no, it's we don't need a paper. It should be on Wikipedia. How do you get the student T? No.
I mean, the paper is short. I mean, it's just 3 pages. So
no. But tell us. But I think we get a student T simply by constraining. Okay, so what happens with the if you constrain the absolute deviation, you get an exponential. The absolute be, if you constrain the log of the deviation, you get a power law. And I think you get a student T by constraining something. It's very easy.
It is. I mean, let me just let me.
No, yeah, go ahead.
Yes, I have the paper here, but I will post the paper on the site.
No, forget about posting the paper. Forget about posting the paper because it may confuse the guys, the people. Yeah, if you get a the maximum entropy by okay, of course you get the Laplace by bounding which is form an exponential by bounding double exponential by absolute value, the absolute value, and then you get a Pareto by bounding log of x, the expectation of log of x, you get a.
Yeah, because I couldn't find the student T on Wikipedia. That's why I looked
Sorry?
for the paper. When I looked at Wikipedia, I couldn't find the student T there, so that's why I looked for the paper. But
Interesting. Interesting. Maybe it's more involved than I thought in finding the
Yes.
student T, because basically student T is a form of power law that turns into Gaussian under the infinite. When the parameter goes to infinity.
Yeah.
The degrees of
Okay.
freedom. Sorry.
No problem. We'll go over that later. So the other approach, Lagrange multipliers, is the approach that this book covers. So the book is interesting in the first chapter, then it's a bit more of a repeated application of the principle with slightly different contexts. We do like that. We do that kind of thing, and we arrive at the exponential. So that's something that we need to go over the detail today, but something that we can also create. Let's say after we work on a bit of that, just post it on the site of the deductions as an example of the method and a guide to do other more complicated distributions.
So Marcus,
yes.
is that used to identify the distribution? So using
yes. Yes, so we just start with the entropy, we define the Lagrangian, and then we start, do all the methods for maximizing everything. So when we go over it, we arrive at
exponential.
The exponential at the end. So this is something that we can. There is a better way of doing that at our live session. It's not this one, but we can cover that later.
Okay, so whichever constraint you add, you solve the Lagrangian.
Yes,
and it gives you the distribution that.
Yes. So the constraint that I gave was so. We minimize the entropy, and then we have two multipliers. One is the condition for the sum of the probabilities equal 1, and then the other constraint is the one of the average, in which I have the probability and the function So this is the main constraint. So when I give the mean constraint here, so this is the mean constraint, I add this term to the Lagrangian, and then I will do this calculation and do all the algebra to solve that. And we arrive at once we arrive here. So for the here, so for x greater or equal to 0. So, but this is something that we can cover on one of the math sessions when we focus more on the maths. So we have those two approaches to estimate the Lagrangian. Now back to Nassim's point about maximum ignorance. So the main problem is, how can we estimate, sorry for the typo, how can we estimate failure rates with never method? One of the points that he raised, can we have enough flexibility in Bayesian priors? So he complains about the beta being too inflexible because the relationship between mean and variance. we might be able later to do some non-parametrical Bayesian stuff to try to see where we can get. So the interesting part about this method is we are trying to model something that has a probability P of success, and the probability has a probability distribution. And we want the probability distribution of this probability to be the maximum entropy probability. So what Nassim does is, for maximum entropy, I want Q to, I want the probability Q to be equal to 1.5, which is the max, as he discussed it before, is the, when I have Q as the probability of success and failure, the maximum entropy is 1.5. And when I do the CDF, it's better regularized, and I want to have the inverse function of that. And because the thing likes to speak about survival functions, then so this is the inverse better regularized as a traditional form. So, but okay, so this is the function that Nassim wants to use. So we have a parameter alpha, which is going to be a half, because which is Q. And when we calculate this function for consecutive successes, so we see that we start, if we start, and if we have one observation, I was okay, one observation is not enough. So I have a success, but I could have had a failure as well. So I still think that the probability of success is a half. But as I decrease, as I increase the number of successes, my estimation of the probability of failure decreases quickly. So go on.
Okay, let me give the intuition for everyone here. Okay, very simple. Let's say it all started with, we're looking at a friend happens to be a surgeon, okay, who does heart transplant. And he did 63 heart transplants without any fluke, that, you know, fluke being defined as operative or post-operative fatality, okay? So his track record is 0 and 63. So how do you analyze empirically his error rate? Okay, so the point is you need to find a method. We have absolutely no background information, because whatever background information, like in the Bayesian framework, it has to be arbitrarily found. Okay, let's assume we don't have any background information. So the way we found out is find P, his error rate, okay, or whatever you want to call it, R, his error rate, such that I'm 50% wrong on that. You see, it's pretty much so. The maximum entropy is half. So let's find a rate at which we're 50% wrong, and 50% probably being above, and 50% probably being below. How do you find that rate? If I assume that the error is binomial, okay, like a 0 and 63, then it's very easy. And typically you can come up with, okay, we expect his error rate to be something like 1.2%. And with time, when you have 1 million, of course, it's going to go to 0. So, and that's very useful for vaccines. Start using it, start working on it at the beginning of the vaccine thing by saying, okay, we're seeing no side effect. What's the probability of having side effect? Okay. And it is, now why is this convenient? Okay. Because in the absence of background information, Bayesian people are a little complicated. They complicate life. Here you get a very neat answer without having to go through Bayesian updating by saying, give me a rate R, which is effectively a probability of error, for which I have 50% error. So that's pretty much the exercise you're doing. So if you go to the graph there, you will see that the next one, yeah, the plot, you see, forget the bands. The bands are just done by because someone was nitpicking because he was upset he didn't come up with that answer. But if you just take what I think is that probability, okay, which I call it the maximum ignorance probability. It already is embedded in a band, which is what the person who asked for a bank didn't understand. I'm taking a jab at someone, okay? That it's already a band. That 50% above is right, 50% below is wrong, and there's no point putting a band, putting more parametric issues on something that complex. Where we're talking about maximum ignorance, and you see how that number drops. It was n. Like we go to 60, what is his error rate? His error rate goes to what? About 1%, no? So if the dot
yes,
zero,
yes, 2%, it's quite low. Yeah.
if that error has 5 different operation and an error rate of 0, we can estimate that the maximum ignorance error rate is 0.1. No?
Yes. So this is on Nassim's blog post. So this is something that we hope to formalize, and we are also want to try a bit of non-parametric Bayesian methods with grids or something to see how far can we go with the Bayesian methods to make a comparison. So this is one of the important issues about maximum entropy methods is to deal with when we don't have the two sides to kind of balance your estimations. Yes, James?
Yes, sorry, I was just going to say, has that comparison with the Bayesian method and the Frequentist method, has that been done in terms of like, yeah.
Compared to the methods, yeah, we answered the frequentist method when you have 0 observation will not assume that there's evidence of 0, right? So the frequentist method, but nobody's stupid enough to use that method to say there's 0 error rate, no potential error rate, and then the Bayesian method is actually worse, believe it or not. And that was my observation. But this converges effectively to the Bayesian method over the long run. And effectively, it would converge to the frequentist in the long run, because eventually if he's going to kill someone, and that would show as 1, and then we'll know the real probability. When the sample size is large. This also concerns the fact that you're dealing with an absence of large sample size, because had the person done 10,000 operations with 0 fatalities, we wouldn't be talking about it. We would be doing something else.
Yeah, so it's like a small data problem.
Right. It's bingo. This is a loss. Now you write the next book after Marcos then.
Yeah. So this is it's always okay. We have let's say small data up to up to 100 or something like that. So how much can we be sure on these circumstances? So we need to get this let's say to show where the Bayesian methods can fail or not. So because if as Nassim points out in his blog post, using a beta distribution is kind of the default for Bayesian, mainly because as a prior conjugate, you can update it in a very simple and fast way. But so if we do not constrain ourselves to the shapes of a beta and we get a bit more freedom in how we parameterize those probabilities, the question is how long do we need to get a meaningful answer?
Yeah, and also another thing. So when Marcos started commenting on my thing by doing his own Mathematica programming, and I looked at it, and that's when I really realized that Bayesian methods are inferior, because basically all you could do is beta method. So he had an excellent example. Marcos provided an excellent example, I think, on Twitter or something, or the beta, how your every time you have n+1, it goes into the parameter of the beta to stay there. It takes a long time for Bayesian thing. And then it's still over time vulnerable to the initial prior.
Yeah.
It doesn't converge, like it's still vulnerable to initial prior and give false confidence. But here we're dealing with maximum ignorance. Bayesian is not dealing with maximum ignorance, it's trying to extract knowledge from whatever statistical framework you have.
Yeah.
So by saying this is maximum ignorance is solves so many issues, just like as with the Brandeis problem by what's his name,
James.
James,
yeah.
who really is a big. Unfortunately, his book came out after he was dead. But he came up with all these ideas of linking Bayesian methods to ignorance, or to entropy, but starting with entropy. And it's unfortunate that we didn't have Mathematica when he published his book and when he did his work, because these are all, as he showed in a dice problem, when you have 6 possibilities, you need a very, very complicated nonlinear, maximization to get the answer that you get in Mathematica numerically in second, which is why it didn't continue. But now that we have Mathematica, we have OpenAI, and we have the participants here who are very, skilled, I'm sure, numerically, you can apply it to many more areas that was not applied. So Jaynes' revenge, this is sort of what I call sort of Jaynes' revenge. We're trying to avenge Jaynes because his techniques were not followed so much. The Brandeis problem is a central problem that's completely ignored because it required a complicated computer then to get the answer, which Marcos got in how many? H of x in 1 second?
1 second, yes, it's quite fast.
Yeah, there you go.
So, and then this is something that I think we identify with. If you want to build a house, you're not going around and asking, okay, you're not discussing whether on average the riverbed is here or 10 centimeters higher or 5 centimeters lower or such. You don't want to know the variance of the level of the river. You go there. This is, I think, if I'm not mistaken, Passau on the Danube. And you look for the high water marks, and for how long have you been following those high water marks? And say, okay, now I think I have information about it to see whether I should build a house here or not. And this is a bit of the idea behind Geman, and Taleb. And when we write Geman, and Taleb, it's not the Geman brothers, it's Elliott Geman and Donald Geman. And so the idea behind it is to look at financial returns, and we start with the VAR constraints. So one thing that we can investigate further is whether to use VAR constraints or CVAR constraints or something like that. So to the VAR constraints, you can choose to add a global mean constraint, an absolute mean constraint, whether the table will follow power laws. On the paper, they started discussing how to apply this to a multi-period framework. And I think that this is one very interesting paper that we need to dive into further detail than today. So one of the things that probably prices of the out of money actions are, they already give me a bit of that. So if if I look at the price of an out-of-the-money option, and if I look at all the framework that was developed in the previous book or something, the out-of-the-money option is already giving me the expected value after a certain point. And when I think about the multi-period, this is a much more complicated part, which is, I hope that everyone is familiar with the story of Joseph in the Bible. He was one of Jacob's sons, and his brothers sold him as a slave, and he ended up in Egypt, and he was imprisoned. And he heard about the Pharaoh's dream about 7 lean cows eating 7 fat cows, 7 lean years of wheat, eating 7 fat years of wheat, and similar stuff. And if we just, if there was a prisoner that would just had said, well, distributions are fatal, you over time you will expect lean years and abundance years, and that's it. That prisoner will still be there in prison until today. What made Joseph successful in being the vizier and because he nailed the order in which those things happened. So, okay, we are going to have the 7 years of abundance and then the 7 years of famine. So the question of whether how the external returns they get together or not over time is probably one of the main challenges in finance. You have some very constrained stuff like a volatility clustering method like GARCH or something similar. You could have just a kind of Levy jumps in which you can have a jump and then you're back to normal. And the problem is that if you look at financial returns, you have all of these and everything else. If you could imagine the market going down 10% and back in the same day and nothing happened afterwards, you say, oh, that's not happening. Okay, that's the flash crash. Oh, you could say, no, if something goes down 20%, you're going to stay there for a while and such. And then you have the post-COVID central bank action that made prices go back quickly in a month and got a lot of people that were kind of trusting that once you go down big, it's slow to get back, and then you get wrong-footed there because you deleverage here, you could not get back here. So getting something that enables you to have this richness of let's say temporal behavior while allowing for some of the properties that we use is a very, very hard problem, and this is one of any challenge of any kind of multi-period distribution that multi-period setup that we do for those distributions. So that paper deserves a separate session because it's a very interesting one, but the math is going to be interesting. And then the last big issue that I would to bring on is the multivariate problem. So there are 2 words that no one likes to read on their financial report: previously uncorrelated. Every time you see those 2 words, that's bad news ahead, because it means that you are trusting that those things will be correlated in a simple way. You're using that your idea that things will behave this way, and you were surprised when they didn't. So it's a pity that Ron is not here because he will have a lot of histories, but James is here, and insurers have all these histories of things. So, for example, there are histories of people writing insurance on NFL games being canceled and saying, "Oh, typically they get canceled because of bad weather, and it's not going to. We're not going to have bad weather in all of the country at the same time on the same weekend because of that." And then something happens like a 9/11 or COVID, and then you have everything gets canceled in a weekend. Or you have the housing crisis in 2008, in which all states fall down at the same time or something. Or more recently, you have the 60-40 portfolio in 2002, in which bonds lost and equities lost, and you are like, "Oh, well, wow, this is not supposed to happen." So I mean, so it's no, you have no. You got too fast with your constraints. If you do it right in terms of maximum entropy, you should not be so quick to get rid of saying those corners are forbidden. I won't have anything happen. I won't have this kind of extreme movement here and extreme movement here. So when you look into multivariate stuff, you should be pretty hard to get rid of the corners. You need pretty strong constraints, and I don't think we have enough confidence to be that strong in those constraints. So this is something to get into more detail once we get all of our toolbox ready with the univariate case. Then it's time to delve into the multivariate case, which is going to be quite hard, because once we start thinking about the possible copulas to link probability distributions, then Mathematica is going to work.
Yeah, I had a question,
yes.
Marcus. Yeah, on this one on the insurance thing. So there's like an insurance problem that I remember where it was how to insure a satellite, so £10 million satellite, and there have been no historic losses, so no crashes of a similar type from that station and so on. So what's the insurance premium? And yeah, so it sounds a little bit similar to that, where there's sort of no historic data.
Oh yeah, yes, exactly. So yeah, so that's why, I mean, it's good to have in this group people who have experience in, let's say, in more directly in financial markets, but also people who have experience in insurance and insurance modeling, because then we can complement each other, and we have not only, let's say, the different data to work on, but also the different methods that we use. So definitely we will need all the expertise of James and Ronald here. So people who have more of a conventional financial background, like myself and Fergal, can work together and learn from it.
I have one comment before. Marcus,
yes.
One second. A footnote from before, when we were looking at the student T distribution, it was obvious and we missed it. They created Renyi entropy supposedly to be able to, because it is the maximum entropy under some parameterization of the Renyi entropy, the non-extensive entropy. So you need non-extensive entropy. So
Okay.
under conventional entropy, it doesn't map. There's no constraint in a conventional way that obtains the student T distribution. But under the Renyi and Salas entropy, certainly, then you have that there's certain parameters that you constrain to get that, or you set at some level to get that. And you also have a probability distribution, the Q Gaussian, that emerges from that.
So we will cover that then. Yes.
Well,
So
we'll
definitely
see later. Completely missed it about Q Gaussian earlier without getting that. Basically, the whole thing is student T doesn't have a Shannon maximum. It's not a Shannon maximum entropy distribution of some conventionally set moments. Sorry, I interrupted for a footnote.
No
I only
problem.
interrupt for footnote and jokes. That's it.
Okay. So this is supposed to be an introduction. So it's definitely not something to go over code or great math deductions. It's just to give an idea to everyone watching about what we're talking about in entropy. So although it's useful to look at the initial stuff about the mathematics that you use to solve Wordle or stuff like that, this is the easy part. I mean, because you know the domain, you typically, the probabilities are chosen typically uniformly. It's not adversarial. You know that there is one correct answer. So these problems are easy. The hard part is we are looking into probability distributions of probabilities. And typically we don't have, let's say, enough data to be sure about things. So when we get some really nice result, it probably means that my constraints are really idealized and it's almost as perhaps in some of the cases almost as ludical as the problem of solving Wordle is. So the fun part is, okay, what do I have in the real world? I don't know things, and I have a limited amount of data that doesn't allow me to look at asymptotic properties or something like that. Also, as usual, when I think about the doctor example, is the data censored in any way? Is the doctor choosing? Am I looking at a doctor that is only choosing which patients he operates on? So if I don't know my case, and I make a decision of operate that, is my decision, do I have that information to know exactly about it? Or if I go into the time series in financial problems, is regime switching something that might work in general for the kind of things that we want to solve in financial returns? So when I look, we definitely want to look at the maximum entropy with environment's paper. We will basically do 1 or 2 sessions which are basically mathematical when we are going through the 2 methods for the exponential, the Gaussian and student T, and see what, okay, now I see the same patterns, the deduction is the same, only this change. Oh, this is the trick to make it work or something. We are going back to the doctor problem to make sure that if we find out that Bayesian methods don't work, at least we will know why they don't, how they don't work, and are they too uncertain to be of any use or not, or do they give me false confidence or something? And definitely once we get over all these things, then we should be ready to delve into the multivariate stuff and start looking at some fun things there. Conclusions, this is just an introduction to maximum entropy methods. The idea is to understand a bit of entropy, use it in practice. We want to leave everything I'll leave the sessions, the further sessions, understanding the properties of distributions and which maximum entropy constraint they relate to. And also understand the value of the absence of a failure, which is the doctor's case, which is, okay, how valuable is that absence? So how much data do I need to? Is it something that I can, is that basic formula applied to any similar problem? Or is it something that will change, or just, okay, I'm going to use that formula to all problems that can be classified as Bernoulli success or failure. So just expanding Nassim's blog post to a paper that compares it with the other methods and say, this is my level of this is how confident am I that I can reduce my ignorance, and by how much, and I cannot be more certain quicker, for example. So establishing those properties is something that is going to be worth doing it. Some of the references, so the blog, last time I checked it, that there was truncated, but I recovered from the Wayback Machine a complete version, including the comments. So there's a PDF on that. So this paper is available on arXiv. The book is interesting. I don't know if everyone should be buying this book. Now we will probably go over the Lagrangian stuff enough that you might look at it, but not sure it's going to be worth the price for everyone who's attending. The last link is definitely worth it because it's free, and it's the Keith Conrad has a lot of explanatory papers in his page. So this one is I found it very interesting because of because the Golomb book focused on the Lagrangian approach, and he focused on the other approach of, okay, what this distribution suggests to you. So I think that we can cover the two approaches. So
one quick comment. I made a mistake with Cauchy. Cauchy, just like the Pareto, you maximize on constraint of log of x, expectation of log of x. Cauchy, you maximize under expectation 1 plus x squared.
Okay.
This is the difference. So, sorry, mistake, but you got always correct. Quickly.
No problem. At the end, we will, when we write out when we go over the math, we will end up quoting Wikipedia and say, okay, for those other distributions, here is the constraint for which they are the maximum entropy distribution for. So definitely we'll have that on a table on the website, so we can always use that as a reference going forward.
Yeah, so sorry to speed up because I guess it's late.
That's it. That's it. So this is meant as an introduction. So definitely details and the hard maths will come up later. So let's stop sharing the screen and we're back.
Let me very quickly say where we can do interesting stuff with entropy, much more intuitive. Say I have correlation. This is correlation between -1 and 1, okay? And let's say 0 here, okay? And let's say I have A here in correlation and B here in correlation, okay? And then we have C, okay? They're equally correlated. When you use entropy message, namely, we're going to talk about mutual information, you may end up having A here. First of all, there's no negative. A here, be here and see all the way here. Okay. Why? We'll discuss later. It's much more natural. People don't get it that when you do a correlation cloud, say correlation of 30%, correlation of 50%, correlation 100%, when you do a correlation cloud, you will notice that a correlation of 75% resembles zero correlation much more than it resembles 100% correlation. So correlation, and even if you square the correlation, you're still not getting that information. So mutual information has other properties, named is additive, and is vastly more applicable in areas like genetics. Like particularly when you do genetic distances, as we just showed here, like some population are a lot closer to one another than you think, and other more remote than indicated by the correlation matrix. And it's all linked to Kelly criterion and horse races. Basically, an association between two random variables A and B is very similar to the association between a horse A and horse B, and how much you should bet on horse B, conditional on A winning. And that gives you the mutual information. It's very intuitive, very linked to Kelly criterion, by the way, and how much we continuously bet on it, not just make one bet, but continuous bets based on that information. So we'll see how it applies to genetics and applies to finance a lot more than you think. Mutual information. Sorry, I'm going to be very, very quick here in thanking Marcos for always going into details of things nobody would think about but Marcos. He finds things that that's like the Sherlock Holmes of our profession. Diligent and meticulous in finding all the wrinkles of all the areas. And again, the uncertainty thing is probably going to be about your book, Marcos, next time. And then we think, okay, of course, the other people. I'll let our friend James close, but I'm saying in which direction we could be heading. I have a paper on why correlation for suckers. It's called Fooled by Correlation, where you can see sub-segments, effectively correlation non-additive. Like if you take 4 quadrants and remove one and the rest, it's not additive. Where mutual information is, and correlation is limited. For example, something like this has 100% dependence. Okay, this is Y, this is X, like a straddle. There's 100% dependence, zero correlation, but mutual information will produce 100% dependence. So you get entropy is better in some areas, but you can't put it everywhere. You can't put it in all sources. You can't really use it for stochastic processes the way it is now. You have to know what to use it for and what it applies. But it applies to many areas in like psychology, where people use IQ distances and stuff that completely be busted by these associations. So the strengths of association between two variables is better assessed by mutual information. And of course we have applications.
Yes, mutual information is something that we need to add to the to-do list. So it's written. I will add it to that.
And also what we call the cross entropy, where entropy of P distribution with respect to Q, the Kullback-Leibniz entropy, and in other words, and this is very intuitive. For example, the correlation between a Frenchman and are you in Lisbon now, Marcos? And between a Frenchman and a Portuguese is different seen from a Frenchman's vantage point than seen from a Portuguese vantage point. It's asymmetric. So you use sum of Q of P log of Q You know, you're weighting the log of one probability distribution by another one, and versus Q log of P. And mutual information basically does both, looking from both sides, look at the joint density. So there are a lot of interesting things, which is very intuitive because it costs a lot more, for example, to turn a Frenchman into a Portuguese than a Portuguese into a Frenchman, for example, or or it may cost a lot more to turn a castle and built in India into the Gothic thing than it would for another one. So basically, these difference got to be seen from the standpoint of one standpoint, not there's no objective standpoint to see them. So you see them with respect to one probability distribution or one cost structure or one unit. So it's very, very interesting philosophically in that sense.
Can it be used for creating like a joint distribution, like in the same way correlation can?
Yeah, because cross here I do it's negative P log of P. No, this one does the following. Okay, mutual information is a double integral. Mutual information f of xy. Okay, log of f of xy. No?
Right.
So by f of x, f of y. Okay. This is how you get mutual information.
Yeah, so definitely, I think that we can discuss later the order in which we cover that. The idea was to first exhaust the univariate case in which we're just looking into one distribution, also to build the toolbox that we need and get familiarized with the mathematics of it. Then we cross over to the mutual information and cross entropy. So it's added already to the list. So we'll look at that before we go into the full multivariate distributions.
Okay. Can I ask if there are any final points? Okay. All right. Well, just to say thank you very much for our hosts, our panel this evening. So Marcus, for that very informative presentation. Thank you for putting that together and talking us through. Nassim for talk. Sorry, go for it. Go for it.
I want to make an announcement. Yeah, just one announcement. Okay. No, after you, when you're done, I just want to make.
Sure, yes. And thank you to Nassim for talking us through many of those points as well, explaining a lot of the background, and also thank you to Fergal and Ron as well for organising, and also the network of consulting actuaries who kindly provided the Zoom. But otherwise, I'll hand over to you, Nassim, for the last word.
Yeah, thanks. No, just to announce that last time we had a meeting, and we jointly produced a paper, Fergal, James, Ronald, Marcos, and myself, in response to TETLOC, and it was published in that journal. So it was interesting, particularly that we had that property that we discovered that will lend itself to more papers. So last meeting was extremely successful in generating a paper.
Yeah,
it was more and more central to the way we view probability. So again, thank you very much, and thanks everyone for participating to that paper, because we had comments online like we do now that were very useful. And then also for next one, address some of Oscar Stiffelman's points, because they seem to be extremely interesting.
Yeah, we'll get in contact with Oscar for perhaps the next session. Otherwise, yeah, okay, so I'll close there, but thank you very much for everybody for attending as well. Thank you. Okay,
Thank
bye.
you.
Thanks. Bye now.
Bye.
I know.